So we have seen test for mean. Let us now move to the test for variance. Okay. So again, in this case also, we are first of all going to import numpy as np, and we will also import scipy.stats module. So we can consider probably the same sample data we had, this one. So sample data is 18.3, 20.1, 19.7, 21.2, 22.5, 20.8, 18.9 and 21.6. And in this case, obviously, sigma naught square will be there, right? So hypothesized value for your variance would be given under the null hypothesis. So we will write null var, that is variance. Let that be 4, suppose, and alpha is 0.05. Now, when you are calculating the sample statistic, you should keep in mind that you are dealing with the test for variance. It means it would require your sample variance, because the chi-square statistic is n-1 times sample variance divided by the hypothesized value, that is null variance over here, sigma naught square. So we will calculate the sample statistics. So the first value could be sample underscore var. So this one would be calculated using numpy's var function, and here we will write this sample data. This is an array containing the observations, and we will calculate the DDOF as 1. Okay, and we can also calculate the sample size. So length of this sample var. Okay, now we will calculate the test statistic. So chi-squared value, that let that be, so it is n-1, right? So sample size -1 into sample variance. So sample underscore var divided by the null var that you have, right? Sigma naught square. Okay, so whatever is the formula, we just go ahead with that. And sorry, this should be not length, sorry, I have written sample data. Yeah. So you have calculated the test statistic. We can also have the degrees of freedom. So degree of freedom is easy to see. It is just sample size -1. Now we will calculate the critical values. So I could use the same thing here. Earlier we used this t-test. Here we would be using your chi-squared. So critical value, right, would be stats dot chi-square dot ppf. So it would be again 1 minus alpha, and here again we would, on the left tail, it would be chi-square ppf. This one will also be chi-square alpha by 2, and this one would be 1 minus alpha, because it is not symmetric. Okay, so in this case we will not just consider minus of that, it would be 1 minus alpha by 2. Okay, so we compare, like chi-square is greater than chi-square u, that is your upper tail value of alpha at the degree of freedom n-1. So you keep in mind that here also we are using this ppf function, so that is why 1 minus alpha is coming. So it will return this chi-square score such that the area to the left of this is 1 minus alpha. So that is why we are writing 1 minus alpha. Okay, it is the way that this particular ppf function is defined in Python. That is why we are writing it is 1 minus alpha. Now we can check for different tests. So let us do the right tail test. So the right tail test, what will happen? We check the condition that if chi-squared value, if this chi-square is greater than critical value underscore right, you will print right tail test, reject H naught, else what you will print? That you fail to reject the null hypothesis. So if you remember from your theory, what we do is, we have chi-square value, this is your upper tail value, so chi-square u, we use this notation, chi-square suffix u was there. If that happens, then you are going to reject the null hypothesis, otherwise you fail to reject the null hypothesis. Likewise, you can write for the other two tests as well, so we could easily just use this. For the left tail test, chi-square would be less than the left value, and here it would be chi-square left tail, right? So it would be chi-square is less than chi-square lower tail value for 1 minus alpha and degrees of freedom n minus 1. So here you would write it as left tail test. So you know the hypothesis also. For different tests, what will be the hypothesis? So here in right tail, the alternative would be that sigma square is greater than 4, because that is your null variance. And in this case, it would be that sigma square is less than 4. Just the reverse of that. And finally, you will have the two-tail test. In two-tail test, we check in either direction. So we will check the value if chi-square, this is less than chi-square value, this one, critical value 2, or if it is on the other side, so chi-square is greater than this critical value, the right tail critical value or the upper tail value. Okay, if that is the case, you would print for the two-tail test, you are going to reject the null hypothesis, otherwise you fail to reject the null hypothesis. This is basically chi-square is less than the left tail critical value, that is chi-square, we used suffix L for this, and in this case, if chi-square is greater than chi-square u, right? So this is based on alpha by 2 and this one is based on 1 minus alpha by 2. So these are your codes. So in all three cases, we fail to reject the null hypothesis, and if we look at the critical value on the right side, that is a right tail critical value, it is 14.06, and what was your chi-square value? It is 3.472. So your chi-square value is actually less than the right tail critical value, so that is why you rejected. Let us look at what happens to the left tail. So it is 2.16. So again, your chi-square value is not less than that. That is why you rejected. And sorry, you fail to reject. It is not rejection, but you fail to reject these. And finally, you will consider for the two-tail test. Let us look what is the value for this. It is 1.68, and to the right, it is 16. And your chi-square value lies in between these two, that is 3.47. So chi-square is neither less than this nor greater than this. So that is why we cannot reject it, and we say that we fail to reject the null hypothesis. So for this same thing, we can also in addition write your p-value approach. So maybe we can add over here only. So let us calculate the p-value for chi-square. So p-value is 1 minus stats dot chi-square, because here we are working with the chi-square distribution, dot CDF. Here you will write chi-squared and the degrees of freedom. So first of all, it will compute the CDF for this chi-squared value that you have obtained here. And since we are interested in the tails, we need to find the probability of observing a chi-square value as extreme as what you have already observed. So you subtract it from 1 and you will get your p-value. Now you have to check if p-value is less than alpha or not. So if p-value is less than alpha, you print reject H0, else print fail to reject. So again it is giving you fail to reject. So let us look what is the p-value here. It is 0.83. Yeah, so p-value, you can see that it is greater than your alpha value, that is 0.05. So that is why you fail to reject the null hypothesis, and you would conclude that it is in fact, in this case, if you see, depending upon whether it is a right tail or left tail, so you can find out the value. Okay. So we are done with the test for variance also. So now last we are going to see the test for proportion. Okay. As you can see, the steps are almost same in all the cases. You just have to be cautious with your test statistic, that whatever is given to you, and then you have to be careful while calculating the critical values. Okay. Test for proportion. So first of all, let us write import this scipy.stats as stats. So let us define success over here, because it is your binomial distribution. So you will have success and the total number of trials. So let me write success as 40, suppose it is 48, right? This is the number of success. And then you will have total number of trials. So total trials, let us suppose it is 100. So you can set up the null hypothesis. So you can consider null proportion as say 0.4. So this is the specified value for the population proportion. So p0, and alpha is, let us take it again as 0.05 only. Now you can calculate the sample proportion. So earlier you were calculating the sample statistic, there was mean and variance was involved, and now you will work with the sample proportion. So you can say sample underscore prop, if I use this, so it would be success divided by total number of trials. And now you are ready to calculate the test statistic, because in this case, what is your test statistic? It will be p hat minus p0, and you divide it by the square root of p0 into 1 minus p0 divided by n. So we have to write this entire thing. So let me write sample prop minus null underscore prop. Okay, sample proportion minus null, that is the hypothesized value. You divide this by, you will have null proportion into 1 minus of that, 1 minus p0, So this one would be again divided by, here we will be one more bracket. So this will be divided by the total number of trials and whole raised to the power 0.5. Okay, so p hat minus p naught divided by p naught into 1 minus p naught divided by total trials and whole raised to the power 0.5, that is square root. Okay, it's correct. So now we can calculate the critical values. So critical values to the right side, it will be stats.norm. We can use norm because it is binomial and we can use the approximation over here. So, and note that there will be no degrees of freedom. Left, again, we'll just replace your chi-square with your normal distribution, and degrees of freedom will also be removed because in normal distribution we do not have it. And this again can be written as minus of this because it is again symmetric. Okay, so minus of what is in the left tailed. Okay, so now you can write the left tail and right tail. If your z star value is greater than critical underscore value underscore right, that is the right tail critical value, in that case what it will print? It will print that is a right tail test. You will reject the null hypothesis. Okay, so you will calculate the z star value, that is a test statistic, and you will compare it with the critical value. If it is greater than that, you will say that you will reject the null hypothesis, else you say that print you fail to reject the null hypothesis. Okay, same thing you can do for your left tailed as well, right? So right tail basically means that we are working with h naught. Null hypothesis would be the proportion is less than the threshold value, that is p naught, and right tail versus your alternative would be that p is greater than p naught, right? So that is why your critical region is defined in this way also. So let us write for your left tailed and two tailed as well. So for left tailed we can write, so here in the left tail we change this critical region, it becomes z star is less than minus of z alpha, so here it would be left tailed value. So this is already negative, so you fail to reject the null hypothesis. Again, if it is two tailed, so here let me make it left and right, left here, for the two tail test we have to look at both the tails. So z star is less than your critical value left tail critical value, or if z star is greater than the right tailed. This is your rejection region. Okay, so you will print that two tail test over here. You will reject it, otherwise you fail to reject the null hypothesis. So once we run this, we find that we fail to reject the null hypothesis. Okay, you can also look at suppose let first of all look at sample proportion. What is sample proportion? Is 0.48 And what is your Z star? It is 1.632. Okay, so your critical value is 1.6448. So Z star actually, it is not greater than your right tail critical value, but is very near. Okay, maybe if you change 1 or 2 values, then it would actually be rejecting the null hypothesis. Again, let us look at the left tail critical value. It is minus 1.644. Okay, so again Z star is not less than that, so we just leave it. We fail to reject it, and likewise you can see that it will happen for the two-tail test also. So basically we have seen the codes for test for single mean, variance and proportion, and in the next week we will look how to write the code for the two sample problem, right? So here you just have that mu naught is greater than mu naught or less than, right? So there you will be considering two populations and the difference between them would be of interest. Okay, so we will see that in the next week. Thank you.